All right, hello to this video series where I introduce the type theory called the calculus of constructions, which is the theory behind the influential, infamous, and difficult to understand proof assistant COC, where COC stands for calculus of constructions, or the more recent versions actually replace the last C with a Q to reference one of the creators, Pieter-Jan, who is an influential mathematician who created this type theory and helped build the proof assistant based on this type theory. And this proof assistant is so influential because it is one of the first ones who utilizes the power of type theory to formalize mathematics in a way that is checkable by a computer. So older systems used a system which depended on set theory, in which every possible mathematical construction is built out of sets. Like, for example, the piano axioms allow us to define numbers, which when looked upon more closely actually are built out of sets. But this introduces a lot of paradoxes, such as numbers being subsets of each other. And if we don't, and for example, sets are very counterintuitive to define rigorously, because as Bertrand Russell showed with his infamous Russell's paradox, intuitive definition of sets actually introduces paradoxes whereby infinite sets that don't contain themselves are paradoxical in nature. And to work around these problems and to make them more applicable to our world of computer science, people have come up with type theories, the forefront of this branch of math being the calculus of constructions. Now, the calculus of constructions is part of a system which extends the simply typed lambda calculus in a couple ways, and usually this is schematized as the Barendrecht cube, which I also will do shortly. And in this video, we're going to define the simply typed lambda calculus as an extension of the lambda calculus. And the lambda calculus is a very concise model for computation, an alternative to the theory of Turing machines. It is a more mathematical definition. It is less operational, but it is more prone to provability. It is easier to make statements about the correctness of lambda terms than it is to do about Turing machines, and especially extensions of Turing machines, which make it more useful, which make the machine in question more useful, but also harder to reason about. So first of all, I'll introduce this new theory of computation, the lambda calculus. So we'll start with an infinite set of variables, V, countably infinite, mind you. So there is it is bijective with the natural numbers, and we use single variables from our usual alphabet, our English alphabet, ABC. And we'll try to not use these variables for any other purpose, such that the notation is unambiguous. And usually we start off this set of variables at the variable x, y, z, comma, dot, dot, dot. And this might wrap around back to A. And then when we're back at X, we might use subscript. So X0, X0, Y1, Z0, and so on. So now we have constructed this infinite set of variables. We can use this to inductively define the set of all strings in a new set called the set capital lambda. And capital lambda is inductively defined, so therefore it is infinite and recursive. So we define this with a context-free grammar in which there are three rules. The rule V for variables, the rule lambda lambda, lambda lambda for application, and the rule lowercase lambda V dot uppercase lambda, which is called the abstraction rule. And these three rules allow us to construct all elements of this set. So, for example, single variables are in this set. So X is just a single term variable. Then X applied, Y applied to X is an application. And then lambda X dot X is an abstraction. And this abstraction rule is really the rule that gives the lambda calculus its unique flavor, because when we will add semantic meaning to this system, you'll see that this is actually a term that depends on the value of another term. And this introduces the concept of dependence, which is detrimental to describing the extensions of the lambda calculus. That will, the biggest of which is the calculus of constructions. All right, so how do these terms compute? Well, to answer that question, we're going to define two equivalence relations, and the quotients over the set capital lambda will actually give us elements of the lambda calculus. So first of all, alpha equivalence corresponds to the meaning of scope. So I'll give you a little demonstration in Python. So define f of x. We'll first define y to be 7, and then define f of x to be return y. All right, in this instance, if we just give any old value, it will always return 7, because at this point in the program, y is actually a free variable, which means it is not bound. And if we define another function, g of x, to be return y, and now we do f of g of 100, it will also give us 7. And in fact, if we do this for I in range 1000, is if f of I does not equal g of I, print I. Oh, it didn't print anything. Therefore, for this very large range of numbers, both f and g compute the same function. And that is why alpha equivalence is defined the way it is. So for variables, free variables are not alpha equivalent. So y and so if we define another variable, z equal to 8, does y equal z? False, right? Because you can look at this as two functions that each have one free variable and they have a different meaning. So free variables cannot be simply renamed because they have semantic value. they have semantic meaning. But binders, in this case, so here f and g both have a binder x, and we could change that variable freely without changing the semantic meaning, which we did here with this I value that goes over this big range. So if we do define f of x to be return x, and define g of x to be return x. Oh wait, we'll do g of y to make it absolutely crystal clear. G of y to be return y. Now, if we do for I in range 1000, if f of I does not equal g of I, print I. Print I. It did not print anything because f and g are always equal. And this is really what is meant by alpha equivalence. We want to keep this property in our system. So therefore, all identity so you can, there's an infinite amount of ways to write the identity function. And here are two examples. And then, so the true identity function is really an element of the quotient of capital lambda with this relation. Now, this gives us a definition for scope. But now, our next equivalence is actually a beta reduction. And beta reductions are really what give us our property of computation. So a reduction of an application, it corresponds to passing parameters to functions. But if y and x are not defined to be functions, the application doesn't make sense. However, if we apply an abstraction, lambda xx, to a variable y, this actually beta reduces. And what it allows us to do is it allows us to fill in this binder and replace this x with whichever thing we pass to it. So in this case, this will beta reduce to y. So here you can see we've actually done a computation. And so beta reduction only makes sense when the thing being applied is an abstraction, and when it might also occur that these definitions overlap, and then beta reduction takes a little detour using alpha to resolve the ambiguity. All right, so now I can give you some more examples. I've actually implemented the lambda calculus myself. So right, so if I now here do lambda xx and we apply it to a variable y, it gives us y. So that is the prototypical example of a beta reduction. And if we do lambda xx and we apply to it this function, wait, right, here we've actually made use of alpha equivalence because these x's introduce different contexts. So in this context, x is, has the De Broglie index of 0, while here it has De Broglie index of 1, which actually is a way of making the variables, giving variables canonical names, which eliminates our problems with alpha equivalence. Every lambda term can be written in a canonical way using De Broglie indexes. And that's actually how I've implemented this. And in that way, we only need to worry about beta reduction. So as you can see here, lambda xxx is it replicates the input parameter and applies it to itself. And if we pass this function, this replication function, into the identity function, we just get the replication function back, which is exactly what we expected. And to show you that this system is powerful enough to express infinite recursion, we'll apply this this application to itself, this replication, self-application to itself, and I think this is going to give us a Stack Overflow, or it's just going to loop forever. Oh, Stack Overflow. So there you can see the lambda calculus actually is able to model infinite recursion. Where is my, oh, all right. So now that we have figured that part out, we're gonna add to this a type system such that self-application is impossible, and we add a new meaning to these terms. So the next thing we're gonna do is define a new set of syntactic constructions and then later on we're going to add meaning to them. So first of all, we so last time we defined a set, we assumed an existence of a set V of X, Y, and so on, but now we're going to assume the existence of a set VT, which contains Greek letters. For this is just for notational convenience. We don't actually. This is actually not significant in the definition of types. Okay. So here, alpha, beta, gamma. Oh, that's another alpha. Gamma, and so on. And we might also index these to make this set countably infinite. Now that we have this type variable system, we can define, set, we can define the set T of types, simple types. So this is again defined by a context-free grammar. So this is elements of VT are elements of T. This is a subset. And we have a new construction, the arrow construction, which gives us function types when we later on add meaning to these terms, which we haven't done yet. So for example, elements of T can be alpha or alpha to alpha, yeah, or alpha to beta. Yeah, and then now we're gonna define, so we have a set of types, and now using that definition, we're gonna define the set lambda, capital lambda arrow. And lambda arrow is also defined using a context-free grammar that has 3 rules. The first rule is type, regular variables. So the set V is assumed, elements of the set V are elements of the set lambda arrow. So X is a set of is an element of lambda arrow. Then application, so lambda arrow applied to lambda arrow. So this might be X applied to Y, is also this syntactic string of characters is an element of this set. And then the last rule, so this is application. Then the last rule, here is where all our pieces of the puzzle will come to play. We start off with a lowercase letter lambda, then a set of the term variables, then a colon, and then elements of the set vt, no, just t. So types, wait, I did it with the bar above. T dot lambda arrow. And what this is the abstraction rule, and what this gives us is, for example, lambda x of type y, of type alpha returns x. And this is a term in this new system, which is an abstraction where the parameters have names, where the parameters have types, excuse me. And we're going to add a few notational conveniences so that we don't have to always explicitly mention all characters in a string. So the first thing is we can omit outer parentheses. So an application and an abstraction both have parentheses surrounding them, but usually from the context it is clear where a term starts and ends, and therefore we can omit these parentheses without introducing ambiguity. So x applied to y. X applied to y is the same as this, x applied to y. Now, the next notational convenience is the associativity of parentheses. So a nested application, XYZ, actually has represents a tree, but in this case, it represents two trees. It represents a leftmost tree and a rightmost tree. And these two trees have different semantic meanings. And the way we work with that is by saying that application is always left associative when we omit parentheses. So XYZ is actually y applied to x and then z applied to the result of that. And this makes it possible for us to omit parentheses in application. And same goes for abstraction. So if we have lambda x, lambda y, x, this is actually, if we wanted to be pedantic about this, we would add parentheses here, but that is actually not obligatory. It's not implied by the notational rules, and therefore we can just omit them. Now, probably the hardest to understand of the notational rules is that of currying. So currying is a system which allows us to define multivariate functions using only single-variate functions by returning a function that takes the next parameter. So if we have lambda x, lambda y, y, this construction can be the notation. Oh yeah, we forgot to add in types here. But since these are just terms of the lambda calculus, we can actually, I'll show you later on how this generalizes to the simple type theory. So this actually is the same as lambda x, y, y. So we have omitted this piece here. And if we add back in our types, lambda x is of type alpha, lambda y is of type beta, and we return y. This is actually the same as lambda x alpha, comma, y beta. Yeah, and we can actually omit this comma as well without introducing ambiguity. And one last thing I forgot to mention is types also have notational simplifications. So, for example, the outer parentheses of a type can be omitted, and the arrow operator is always right associative. So alpha implies beta, implies gamma. Is actually defined like this, right? Where the outer parentheses can be dropped because outer parentheses can always be omitted, like I said earlier for terms, but these are types. And the arrow is right associative. So a tree of arrows always associates to the right if we omit parentheses. So alpha goes to beta goes to gamma, associates like this, while if we add parentheses here, this is a different tree, which associates to the left. But we define it as associating to the right because then the associativity of application and types actually cancel each other out. And I'll show you how that works. In this implementation I made of the simple type theory. So if we enter here a term, lambda x of a, comma y of b, which gives us back x. We could even have omitted the outer parentheses. This is of type a to b to a, right? Here, I should have done application actually. But here you can already see types associate to the right. And now if we do, we actually need to introduce a new concept. So as you can see, this line I've entered here consists of three parts. The first is this new character here, which means derives. If we actually write something before that character, x of a, y of b, or we'll do x goes from a to b, y of type b derives x applied to y of type b. Yeah, like that. Here we have actually stipulated a type check question. So everything that comes before the derives statement is a list of type variables with their associated types. And this is called the context. And you can kind of think of this as a list of binders to an abstraction, but this is on a higher level. Then this middle part is the term that we are talking about, and the rightmost part is the type associated to this term. And both of these together is called are called a statement. Now a judgment, which is a whole line like this, is correct when beta reduction defined in the way as we did before checks out, so the types line up. For example, here it says type error in application because we tried to give an element of type beta to the function x, which goes from alpha to beta. So beta and alpha are not equal. Therefore, it did not work out. However, here it did work out. And that's why this judgment gets parsed and derived in our system. And we even, the system gives us a little proof of why this works. And this is how we can use this system to talk about proofs. So the type theory is built around a very deep correspondence between proofs and programs called the Curry-Howard correspondence. And Curry-Howard, the Curry-Howard isomorphism can be summarized by an ambiguous acronym, TAP, where TAP has two interpretations. So the T may stand for terms as propositions, or it may stand for no, that should have been types as propositions. We'll give that a bullet. And terms as proofs. I'll enlarge that. Oh, that's not what I wanted. Boom. Oh. Wait. All right, so we've just defined terms, and we've seen that a tautology such as A goes to B goes to A has an associated term, and this term can really be seen as a summary of the proof of this type. And this the question mark here represents a problem called type inhabitation, which is really the fundamental problem that Koch tries to solve. And for the simple type theory, it is a decidable problem. As you can see, I've actually made a program that solves instances of this problem. But for the bigger type theory, such as the calculus of construction, this is actually undecidable. And that's why you need to be creative when solving this, because terms in this context actually correspond to proofs or inhabitants of this proposition. And that's how we get these two coinciding meanings of this acronym TAP. And this is obviously an inhabitant of this type because it is a tautology, and we have not introduced any assumptions, which would be a context. Let's try adding a context. So x goes from A to B to C. Z is of type A. Y is of type B. And then we ask, can we build something of type C? Oh. Okay, so that was actually a, it cannot do nested application yet. But if I enter this term search, it's going to tell me, okay, you can just apply x to z to get something of type beta. And the following is a proof of that. So as you can see, we have defined the simple type theory, in which terms can depend on other terms, using abstraction. And we can prove very simple propositions in this system. And the implementation gives us a derivation if we give it a judgment to type check. So I'll also, as a last demo, I'll give you a derivation which does not compute because the terms don't line up. If we, for example, we have a type x from a to b, and we have another variable of type b, or we'll do c just to be absolutely clear about this. And if we apply x to z, and we then stipulate that this the application of this term gives us something of type b, that's going to say, oh, that is a type error there is a type error in your application because z is of type psi and x wants something from type alpha, and that's why that doesn't work. And all right, so I think that concludes the introduction of the simple type theory. Later on, we'll extend this type theory in 3 ways and combine all these extensions to give us the calculus of constructions, which will then give us a deep understanding into the Coq proof system. So I'll see you then, and you can check out my implementation on GitHub. All right.